Okay, think about this for a second. You're watching an NBA game, maybe paused it right during a scramble under the hoop, trying to pick out one player. I mean, it's tough even for us, right? The blur, players crashing together, same
Oh,
uniforms.
absolutely. It's basically a nightmare scenario for computer vision. You've
Yeah,
got super high speed, bodies blocking each other constantly. That's occlusion, and the camera's zooming and panning all over the place.
right. It makes just recognizing who is who incredibly difficult for any automated system.
A massive challenge.
So today we're going to unpack exactly that for you. We're diving into the sources that lay out this really complex multimodal AI pipeline. It's engineered specifically to tackle these problems.
Yeah, the goal is to see how they string together different AI models to, first find the players, then track them, and finally figure out who they are by their jersey number.
Okay, so step one, detection, just getting eyes on the players and the ball. The sources mention using something called RFDETR. Why that specific model? Not, say, the usual YOLO.
Well, RFDTR is apparently quite good, quite accurate, but also fast. And it's not just finding person. It's trained to spot specific things like player jump shot.
Ah, okay, so that extra detail helps it cut through the chaos, the motion blur, and overlap better than a more general detector might.
Exactly. It gives a much stronger starting point, even when the video feed is, well, messy.
Got it. So you've detected them. Now the really tricky part, tracking them when they disappear. That brings in SAM2, the segment anything model 2. How does it handle players vanishing behind others?
This is where it gets clever. They use what they call a temporal memory bank.
Temporal memory bank.
Okay. Yeah, think of it like this. SAM2 sees a player, notes their visual signature height, maybe how they move, where they were. It stores that.
Like a little memory file for each player?
Pretty much. So when that player gets blocked, say by another player or the ref, the system holds onto that memory the second they reappear, even partially.
It checks the memory bank and says, that's player number 23 again.
Exactly. It re-identifies them almost instantly. That keeps the tracking solid, even with all the, visual interruptions. Really helps maintain consistency.
That is smart. Very smart. Okay, before we get to actually reading the numbers, let's quickly mention our sponsor. If you're looking into AI, whether it's getting your team up to speed or actually integrating these kinds of technologies, embersilk.com is your resource. They cover AI education and integration needs. Check them out at embersilk.com.
Right, so we're tracking individuals now, but the system still needs to know which team is which. And you can't sit there labeling uniforms for every single game, obviously.
No way. That's not scalable. So how does it figure out Team A versus Team B automatically, just by looking?
It uses visual similarity. They employ a model called SigLep to look at the players it's tracking and essentially turn their uniform appearance, color, texture into high-dimensional data points.
Okay, so each player becomes a point in this sort of data space.
Kind of, yeah. Then they use a technique called UMA to simplify that data, reduce the dimensions, make it easier to handle. And finally, a standard algorithm, K-means clustering, just splits all those points into two groups.
Based purely on how similar the uniforms looked in that data.
Exactly.
Yeah.
It automatically clusters them into Team A and Team B without any prior labels.
Yeah.
Pretty neat generalized solution.
Okay, detection, tracking, team assignment. Now the moment of truth. Reading the jersey number. Tiny text, often blurry, maybe partially hidden. The sources mentioned they tried two main ways for this, the OCR part.
They did, and this was interesting. First, they tried small VLM2, which is a vision language model. It's sort of a generalist AI. They fine-tuned it and got 86% accuracy. Not bad.
Okay.
But then they tried a much simpler, more specialized approach. A convolutional neural network, a ResNet, trained only to classify those jersey numbers. It blew the VLM away, got 93% accuracy on their test set.
Wow. So the specialized tool really nailed it. Sometimes simpler is better, huh?
It really seems so in this case.
Yeah.
Focus beats generalization sometimes.
So once it thinks it sees a number, say 23, how does it make absolutely sure that number belongs to the player mask it's looking at and isn't just like a sign in the crowd?
Good question. They use a metric called iOS intersection over smaller area. Basically, it checks how much of the detected number's bounding box is inside the player's segmented mask.
And there's a threshold?
Yep. The match is only confirmed if the iOS is 0.9 or higher. So the number has to be at least 90% contained within the player's outline. That filters out noise really well.
Makes sense. And they don't just trust one frame, right? There was something about stabilization.
Correct. They built in a heuristic for reliability. A player's identified number, say LeBron James 23, is only locked in once the system sees that same number 23 predicted for that player 3 times in a row across the sampled frames.
Adds a layer of certainty. Prevents momentary glitches from causing a misidentification.
Precisely. It ensures the final roster mapping is stable.
So, putting it all together, we have this intricate pipeline. RFDETR for detection, SAM2 with memory for tracking, SigLep and k-means for teams, ResNet for numbers, and iOS plus stabilization for the final ID. It works.
It does work. The sources demonstrate feasibility, which was the main goal. But, and this is important for you to know, there's a big caveat right now. Speed, yeah. The whole system currently runs pretty slow. We're talking maybe 1 or 2 frames per second on a decent GPU, like an NVIDIA T4. The main bottleneck seems to be SAM2, the tracking part.
Okay, so it's not ready for live broadcast integration just yet.
Not for real time, no.
Yeah.
But the core engineering problem, can we reliably identify every player, even in chaotic conditions? The answer seems to be yes. They've shown how it can be done.
And that leads to the really mind-bending question, doesn't it? What if this could run in real time, like 60 frames per second?
Exactly. Imagine the level of analysis coaches and strategists could have. Not just knowing who scored, but the exact position, posture, and context of every single player on the court for every single action. Who set the screen, who was slow rotating, who made the subtle cut.
It would fundamentally change how teams prepare and analyze games. You're moving beyond basic stats into, like, micro-interaction analysis.
It opens up a whole new dimension of strategic insight, insights that are just invisible to the human eye or traditional stat sheets right now.
A fascinating glimpse into what computer vision might bring to sports analytics down the road. Well, that's our deep dive for today. Thanks for exploring this complex AI pipeline with us.
Always interesting stuff.
If you enjoyed unpacking this, please consider subscribing to the deep dive. And hey, maybe leave us a 5-star review. It genuinely helps us out a lot. We'll catch you on the next one.